Ladies and gentlemen, for my next trick, we will try and integrate an antiderivative that doesn't seem to work for integration by parts. We don't seem to have a dv, but we're just gonna coax it a little bit, play around a little bit until we can integrate. So here's the integral of x cubed e to the x squared dx. And your first thought might be, oh, let me try u sub, because I've got an inside function here. So maybe its derivative is on the outside, but slight problem with that. The derivative of x squared would be 2x, which is linear, just 1x, but I've got a cubic out here. So there is a way to finagle that, make it work, but you know what? We'll save that for another time. We'll just say that doesn't really work. So instead, we'll say, all right, let's try integration by parts. And so we've got the first part of integration by parts. We love to see these powers here because we know that those can be our u's and they will differentiate themselves away into oblivion in just a couple of steps, and that's great. But if we're going to do that, the problem is then we would need a dv, and to say that e to the x squared dx is our dv, that's a bit of a problem because e to the x squared doesn't integrate nicely. So it couldn't really be my dv. But like I just said a second ago, if we think of e to the x squared with u substitution where x squared is on the inside, then all we need is an x on the outside, and we would have been able to integrate. So x e to the x squared will integrate nice and smoothly using u substitution. Well, what we can do is take our x cubed e to the x squared and kind of separate some of those x's. If I want to be able to integrate my dv and I need an x, well, I can borrow one of the x's from x cubed and write that as e to the x squared dx. That I can integrate. And if I've taken one of the x's from x cubed, well, what I'm left with is x squared. And so I can set up my u substitution, my integration by parts. We'll differentiate down the first column. The derivative of x squared is 2x, and we'll integrate the second column. It is completely fine. In fact, it's kind of normal if you kind of need to write this out a little bit on the side. I'm going to write my u sub over here on the right. If my u is equal to x squared, then my du is equal to 2x dx. So if I want to take the integral of x e to the x squared dx, I'm going to need to put a 1/2 in front of it, so I can have the 2. And then its antiderivative will be, so then it becomes the 1/2 times the integral of e to the u du, which is just e to the u over 2. And we know that u is x squared, so that's e to the x squared over 2. So that will be our antiderivative there. If you are kind of a little bit more comfortable manipulating all that in your head, that's okay. You can feel free to do that. Just do be really careful about that over 2. It's easy to forget that we need that coefficient there. So our v, our antiderivative of our dv, will be e to the x squared over 2. And if we're trying to do this using rapid repeated integration by parts, we've got a little bit of a problem here. The problem is that I now have another dv that can't be integrated. I would need to have that x in front, just like we saw before. But we can do a sneaky little thing here, and this is something we can do every time we're doing rapid repeated integration by parts. If we come to a dv that we need a little bit of help with or something like that, or a u that's too complicated to differentiate, we want to cut something away, we can always reassociate the factors from the du to the v in the same row. So that's what I'm going to do. You do have to be careful, and it gets a little bit weird here. You have to make sure to show that I'm not doing my differentiating one column, integrating the other. I'm not doing that in this next step. All that I'm doing is taking the x from this column and moving it over to that column. Now, while I'm at it, I might as well take the 2 also, because it'll cancel out the over 2 in the other column. So what I'll be left with here is 1. And in the other column, I now have x e to the x squared dx. And that looks familiar. So now when I keep doing my rapid repeated integration by parts, I will differentiate my u column, integrate my dv column, and we already know what this is because we just did this. Sorry, I had forgotten that dx all along because I said with the rapid repeated integration by parts, we don't usually use it. I wanted to include it in this case just to show you what's happening in the background. And so what we can do now is use our connections, right? We're talking about the product of uv, that's this guy, and then the product of our next uv, but remember we're going to have to switch the sign on this one. So the key here is that I don't connect these two because I did another row of my u and my dv to get to this row here. So I can't connect the diagonal before that. I've got 2 diagonals to connect here, and that's it. So then my final answer here will be the antiderivative of x cubed e to the x squared in respect to x is my first diagonal, x squared e to the x squared over 2, minus my second diagonal, e to the x over 2. And then the last step, I'm not going to write this out the long way, would be minus the integral of 0. Well, the integral of 0 is just some constant. So that's where my plus c comes in. And that's the process that we call reassociating